Okay, kids, here it is. Unit 9 series. Congratulations for getting here, right? Think of how much calculus we have already done. And you are at series. Again, if you were in AB calculus, you would be done with the course by now. So here we go. All right. So what makes series hard, I think, is the fact that there is lots of algebra in it. Lots of algebra, and that what you're actually doing is very abstract. The concept of what you're doing with all that algebra is very abstract. You know, like if you were, oh, my Google is answering me. If you think about back to your Algebra 1 experience, though, when you first were factoring quadratics, right? Think how normal that seems to you right now. Factoring a quadratic to find x-intercepts, right? Giving you x-intercepts, write a quadratic, write the general, right? That was pretty abstract when you first learned it. But, right, so series, hopefully now that's not as abstract. It seems pretty normal. Series is outside your norm. It's going to feel very weird. When you're done with this unit, if you say, I understand series, I'm not going to believe you. It takes a lot of time to actually understand what you're doing with series. So your goal right now is to try to just get the algebra down and worry about the abstractness. Try to put that aside for now. No one's going to ask you to interpret series yet, right? Not this year. You don't need to understand what series is unless you're actually going to use this in your major in college. You just need to, if that's not you, then you just need to get through this and deal with the algebra. All right, here we go. Improper integrals is actually not part of the series unit in your book. So when you look at this homework page, you're going to say, why aren't I in the series unit? But we like to put improper integrals at the beginning of the series unit because conceptually it's an abstract concept. And the algebra that you do with improper integrals is going to help you with what we're going to be doing in series. So we're actually not going to start true series, for a couple of lessons. So if you have your calculator and you want to do this exercise with me, that's great. If you want to skip it, great. But if you put into y1 e to the negative x squared, x over 2, and then use a function that we haven't really used before. Mostly when I ask you to do an integral, you use Math 9. I don't want you to use Math 9. I'm trying to help you with the visualization of what's going on. I don't want you to use Math 9. I want you to plug this into y1, then go to your graph and hit second trace, and then look at choice 7. Choice 7 is an integral. When you choose that, what does it ask you for? Lower limit, right? So I want you to put in 0 as your lower limit. And then I want you to and then when you hit enter, what happens? It asks you for the upper. And I want you to put in 3. And you're going to get a number. Okay? Now I want you to hit, and what's nice though is that shades it for you, doesn't it? Do you see the nice little picture that you get? This is the concept that I'm talking about. Right, so you got this picture from 0 to 3. I want you to go back to your home screen, and I want you to hit second mem, right? I want you to do, I guess that won't work with this. I just want you to hit second trace 7 again. And I want you to hit a lower limit of 0 and then a lower limit of 5. And what are you going to see? You're going to cover more, right? And you're going to get a number. Is that number bigger or smaller than the number you got before? You got a bigger number, didn't you? Now repeat it with 0 and 4 and 0 to 10. And I hope that the concept that I'm trying to get you to go to is that, I don't know why they meant to put 4 here. 10 here. Hopefully you do know from Algebra 2 the asymptotic behavior of this function. This function approaches 0 but never ever gets there. So you don't actually have a closed interval until you say stop at 3, until you say stop at 5, until you say stop at 4, until you say stop at 10. And I could even say 100, couldn't I? And each time that you're doing this, right, each time you increase, you go from 3 to 5 to 10, you get a bigger and bigger number. But what do you notice about the jump? How much bigger? The magnitude, right? And I'm going to make up completely random numbers here, but let's say that this is, right, 5, which I know it's not. And this is bigger, but it's 6. This is bigger, but it's like 6.1. So notice the, right, as you go further and further out there, because this function is falling to the asymptote at the x-axis, but never hits it, you still are going to, right, if I asked you to do this, 0 to 1 million of e to the x over 2 dx, you would get a number because I stopped you. I bounded the area, but I hope you won't be surprised if I say you're going to get a number like 6.00001 here, right? So this is where we're going. What if I said, what is the limit as 0 goes to infinity? Whoa, what is that? 0 to infinity. You say to yourself, self, that's a problem. But, gosh darn it. But that's not bounded area. You're right, it's not. That's what makes this integral improper. You can't do a proper definite integral unless you have a definite start and a definite stop, and infinity is not a stop. So I put this, this screenshot of my calculator is when I was doing math, second trace 7, and I put all these numbers in here, right? So when I went from 0 to 3, I got about 1.5. 0 to 4, I got 1.7. 0 to 5, I got 1.8. 0 to 10, I got 1.96. I covered up 20. But it's down here, 1.9999. So what is your prediction? What do you think as you get the rectangles that you're drawing are going to get smaller and smaller and smaller? Smaller and smaller, but you're still adding them. There still are rectangles way out here, way out here. There's still rectangles, so you're still adding, but you're adding to a ceiling that you will never bust out of. Hopefully you're not surprised by the fact that this is 2. 2 is the answer to that improper integral. And the question is, how do I get 2 without using my calculator and doing this guessing? I want a mathematical way to get the answer of 2 for an improper integral. So accumulating the area under the curve from 0 to infinity, no matter, isn't that kind of crazy? I mean, that's kind of cool. No matter how far out you go, you're going to be adding such an infinitesimally small amount that you will never get above 2. I think of this kind of like a house, right? Where I've got a house and there's a ceiling and I'm adding, right? I keep stacking values. Maybe this is my shed where I'm stacking wood and I'm stacking, covering up. But the wood that I'm adding is so infinitesimally thin here, I will never get above the ceiling of the house. Never, no matter, even if I keep forever adding wood, right? I will never get above a sum of 2. So I got to prove this. How do you think I prove it? Well, if I'm thinking about accumulating area, that's what my integral is doing, accumulating. The area, that sum, goes off forever and ever, gets really close to what L word? Limit. So an improper integral, type 1, this goes, you have a note sheet that gives you lots of space to write because you want to try to classify your improper integrals. An improper integral is like, oh my gosh, I'm so embarrassed. Look, I don't have a number up there. I've got an infinity. That's so embarrassing. My infinity sign is showing, right? So if you have an infinity as a limit of integration, that's type 1. That is the most common on AP free response. We often see an improper integral embedded somewhere in a free response problem. Not that it won't show up on multiple choice, but this is the most common one. So we're going to spend the most amount of time on type 1. So there's, firstly, you got to identify your improperness. Recognize you have an improper integral. You're going to replace infinity with a dummy variable. That's not a very PC term, but it's what your book uses, what they all use it, right? I just say replace it with a variable. And then you're going to ignore the infinity part. So take the infinity sign, replace it with a variable or a letter, really, not even a variable. And then you're going to take the limit, but notice where my infinity sign shows up now. Right? I just took infinity, replaced infinity with a, and then said I'm going to take the limit as this number approaches. Then I'm going to treat that number a like I did in that previous example, right? Where we were using our calculator, 0 to 3, 0 to 10, 0 to 20. That's what I'm going to pretend a is. And I'm going to second fundamental theorem that, or the second part of the fundamental theorem, or the integral evaluation theorem. Then I'm going to evaluate the limit, right? So see how my green box here is around just the integral part and ignores the limit. Then after I get an expression, right? Because after all, the integral evaluation theorem takes your integral and gives you an algebra expression. I'm going to get an algebra expression with a in it. I'm going to replace a with infinity, evaluate the limit. Remember, when you evaluate a limit, you either get a number or an infinity or it does not exist. If you are able to evaluate the limit and get a number, you say your improper integral converges. And when you think converges, I want you to think house, right? The top of the house. Converging, meaning you never get above the ceiling. No matter how much you're adding, you always stay in the house. Okay? If you get an infinity, or you're not going to get it, does not exist. If you get an infinity, though, then I need you to think your limit busts out the house, right? You don't have a ceiling. When your summing values aren't small enough to stay under the ceiling, and they'll bust out the house. Okay, important. So let's go. You ready? So I saw my improper integral first. I took my, step 1. Recognize, remember this started out as an infinity. Shouldn't have covered it up. So step 1, recognize improper. I forgot my music was on. Okay, Google, stop. I'm going to focus just on the green part. I'm going to ignore the limit. Recognize improper, set up the limit. 2, ignore the limit. and do calculus. So how do you integrate e to the stuff? Right? Hopefully you don't really have to write all this out, but you recognize that there's your u, here's your du, multiply, blah, 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 blah. At this point, your integration should be kind of fast. Again, still ignoring the limit. There's my -2 du, e to the u. Anti-differentiate e to the u. I don't know why that came out that way. What am I going to evaluate this at? I'm going to evaluate it at 0 and a, right? 0 and a. Plug an a in for x, plug a 0 in for x, subtract, multiply by -2. So this is now step 3. You're almost ready for step 3. You have plugged in, you've done the second, right? Calculus, the integral evaluation theorem. E to the 0, you know what that is. There's my 1. I still really haven't thought about my limit yet. I've done all I can, but I still now have this a in here. There's nothing I can do with that. Actually, I rewrote it, and you don't have to do it this way, but right, e to the negative exponent is the same as reciprocate your base and negatize your exponent. So I dropped e into the denominator and changed the sign. The reason I did that is because notice the limit notation is now uncovered. This is step 3. Now I'm going to evaluate the limit. So into here, here's what you have to think. What are you putting in for a? You're putting in infinity. What's infinity divided by 2? Freaking still infinity. What's e to infinity? Infinity. What is 1 divided by really, really big numbers? Okay, did you hear all of that thinking process? Let me say it again. So I say to myself, self. 1 over e to the big over 2 is 1 over e to the big, which is 1 over something really, really big, and 1 over something really, really big approaches 0. Right? So I put e to the really, really, really big divided by 2 is still e to the really, really big. E to the really, really big is big. 1 over something really, really big approaches 0. So now what do I have in there? 0 minus 1 is -1. -2 times -1 is 2 OMG. That's what we had guessed, remember? From our calculator. That's how you evaluate an improper integral type 1, which is where you have infinity as an upper limit of integration. So my conclusion is this improper, oh, Duke, stop. This improper integral converges, which means the sum, the infinite sum under this function stays in the house. Stays in the house, okay? Notice that, side note, I hope it doesn't take too much imagination for you to say that this improper integral busts out the house, right? Here's my graph, x squared goes on forever and ever. So the area, the sum under this curve will never stop growing. This sum, right, this is the house with my sum. I start adding those rectangles, the house cannot contain it, it busts out the house. It looks like a rocket. Right? Now, something that continuity is important, even though this was not a closed interval, so I had to deal with the fact that I had an improper here, but I did have continuity from A to infinity. So I do have to, if I'm going to write, I can't deal with yet improperness on both sides. So here's another one. Now, in our live session, I'll do an example where we have another type 1 where an infinity is at the bottom, right? So I go from negative infinity to 2 or something. I'll do that. But I wanted to, just in this video, skip to this dagger one. I mean, what is happening? I've got double improperness. Oh my gosh, I've got infinities showing everywhere. Ah! Right? What the hee-haw? Now notice this function is continuous everywhere, right? Because even though it's a fraction, the denominator is never equal to 0. So I've just got 2 problems I have to do. Whoops. The first problem, I'm gonna use the property of integrals, which lets me break up an integral. And if I'm gonna break up an integral, why wouldn't I break it up at 0? So I'm going to do one limit as my improperness is at the bottom. And I'm going to do another one where my improperness is at the top, and I'm going to add them together, right? And you're like, wait, what, how? This is the properties of integrals, right? You know from a long time ago that, oh gosh, darn it. Let's do that. The integral from A to B plus the integral from B to C is the integral from A to C, right? So if you're going to break up an integral that goes from A to C, and for me, that's negative infinity to infinity, I'm going to break it up somewhere. Why wouldn't I break it up at 0? Since I'm going from negative infinity to infinity anyway. So now I've just got 2 improper things. So this is a nice one because I can practice. Oh, snap. Did you see that one coming? Remember, I'm ignoring the limit part. Once I write it down, I ignore it. Ignore, ignore. Right? I wrote it down, then ignore. I look at this as a fraction. I can't unquotient it, so I don't think partial fractions first, right? I think, is this on my list? And yes, it is. It is inverse tangent. So this one is also inverse tangent. But notice my limits of integration are 0 and A here, but A and 0 here. Now, you're going to put in 0, and I hope you can evaluate that. Who has a tangent of 0? And we are in function land, so I'm not going to get more than one answer for that. Who has a tangent that is 0? Good. 0, right? But this one, this takes a graph, and you don't have a calculator. You have to know graphically, where does inverse tangent go to the far left? Oh my gosh, I don't know. How am I supposed to remember that? Okay, maybe you don't, but you best freaking remember what tangent looks like, gosh darn it. Tangent looks like this. Asymptotes, vertical, at the pi over 2's. How many times did I make you label this in your pre-calc class, in your algebra 2 class, right? It looks like a trapped cubic. It's not cubic because it doesn't expand forever. It's trapped in jail by the pi over 2's. What's the number one fun fact about inverses? X and Y are switched. Put that freaking, this is inverse tangent, not tangent. How did I get negative pi over 2? Because the graph of inverse tangent, for God's sakes, Oh, shoot, I thought I kept clicking because I thought I had the picture of it, but I don't. The graph of inverse tangent, this is tangent, inverse tangent, doesn't have vertical asymptotes at the pi/2's. You know what it has? It freaking has horizontal asymptotes. Prerequisite classes are prerequisites for a reason. So where does inverse tangent go to negative infinity? Negative pi/2. Where does inverse tangent go? Sorry. Where does inverse tangent go when you're going to positive infinity? Pi/2. And then, of course, inverse tangent of 0 is still 0. OMG. Pi. If you knew about the symmetry, if you also could figure out the symmetry, you could only do this once and multiply by 2. Right? So many things that come back from prerequisite classes. Oh, snap. So since I got a number, remember, if you do an improper integral and evaluate it, and you get a number, you're allowed to say you stayed in the house. So this sum of all of the rectangles from freaking negative infinity to infinity, the sum of an infinite amount of rectangles forever going across an entire domain is pi. I mean, and you know what today is? I'm making this video on Pi Day. Ha! Getting a little out of hand, sorry. All right, let's do another one. This is an improper integral. Step 1, identify. I have improperness. Step 2, set up, ignore, do calculus. Okay, so I set up the limit. I replace the improperness with an A. Now I'm going to ignore the limit and I'm going to do calculus. The antiderivative of 1 over x is ln of x. I'm still going to ignore the limit part. I'm going to do the integral evaluation theorem. ln of a minus ln of 1. Hope you know that ln of 1 is 0. Was still ignoring the limit. Then I said to myself, what is the graph as I'm going off to infinity? What does the graph of ln of a do? Well, it doesn't grow quickly, but it keeps growing forever. So when I think about the limit, after I evaluated that to be 0, now I thought about the limit and said, what happens to the graph of ln as I go off to infinity? Duke, stop. He's barking at a tree. He's barking at the wind blowing. So that answer was infinity. Is infinity a number? That limit was infinity. Is infinity a number? I don't think so. Therefore, this improper integral diverges. Come here, puppy. Come here. Stop. Stop. There's nothing out there. Nothing out there. Be calm. See? Sorry, kids. I'm coming back. Just had to shut the windows so he doesn't bark at the tree. He's such a good dog. You know, and if you walked in my house and decided, right, just a stranger coming inside my house, he would not pay you any mind at all. He wouldn't even look at you. Oh, dogs. Oh, I love you, Duke. Yes, I do. Okay, so here is the graph. Now, I started my graph at, hey, why did I start at 1, do you think? Because there's a vertical asymptote there, right? So I had to start where I could have started at 0.01. Doesn't matter. Going off to infinity. Going from 1 to infinity of 1 over x. So I started here. Even though this function is right falling, the fact is, I mean, it looks like it's kind of right. Those numbers are getting smaller and smaller. They're just not getting smaller at a fast enough rate, right? So this function does approach the horizontal asymptote y equals 0, just doesn't do it fast enough. To converge. These first numbers here are too big. They're too big, right? So even though these sums get really, really small as you go off to infinity, the first numbers were way too big so that when you started adding smaller and smaller numbers, they busted out the house. Bust out. Getting an infinity as an answer to my improper integral limit told me that. So we say this integral diverges. Diverges means can't be contained, baby. All right, type 2. You say to yourself, self, this does not look improper. You took algebra and you paid attention, and you know the domain of this integral. Here is my improperness. This is improper because there's a vertical asymptote at a limit of integration. This is very common. On a multiple choice AP exam. 2 points down the drain, because you can evaluate this with the integral evaluation theorem. You can plug in 1, you can plug in 0, and you're going to get a number, and that number will be one of the choices. It'll probably be choice A. But that would be nonsense because you can't plug in 0. So step 1 is still recognize. I've got an improperness, then you have to replace it. So here's this function. It does approach a horizontal asymptote at y equals 0. My math will tell me whether it collapses fast enough to that horizontal asymptote or not, and I have to avoid the vertical asymptote. So there's my improperness. Replace it. I don't have to replace the 1. Notice this here, right? Because I started at 0, it's just the, right? I just have to take the limit as I approach 0 from the right. I'm ignoring the limit, ignoring the limit, ignoring the limit. Gonna plug in 1, gonna plug in A. Evaluate, still ignore the limit while you evaluate this. 1 to power of a half is still 1, times 2 is 2. Now go over here and do the limit work. Right, do you see what I did there? When I plug in a number like 0.00001 in for A, the square root of something really, really close to 0 is really, really close to 0, and I am plugging in a number from 0 from the right, so I'm not going to plug in a negative, so I don't have to worry about taking the square root of a negative. That's 0. Negative 2 times 0 is 0. I get 2. Just a coincidence with our other function that got 2. Now, you might say to yourself, hey, if I didn't recognize this improper integral at all, and I just did this as it was, and I plugged in, right? I plugged in 0, I would still get 2. Yes, you would have in this case. Yes, you would have. But trust me, on AP, they're not going to give you one where that happens. Type 3. Right, so I left plenty of space on your note sheet for you to write for more examples that we can do of type 1, 2, or 3. But in the video, I'm just doing a couple here. So this time you look at 0 and you look at 3 and you look at x and you're like, oh, plugging in 0 is fine, plugging in 3 is fine. Why is this improper? Well, that's because x equals 1 is the vertical asymptote, right? And 1 happens to be between 0 and 3. There would be nothing improper about this if I was going from 2 to 3. But because my vertical asymptote is in the middle, this is improper. Well, then how do I replace it? Where do I put my improperness? I have to do 2 again. I have to go from 0 to the improper integral, to the vertical asymptote, and then the vertical asymptote to the stop. So you have to break it up. This time I don't get a choice of where to break it up. I have to break it up at the vertical asymptote. And then I just have to do math. Notice here I'm approaching 1 from the left. Over here I'm approaching 1 from the right. Integrate, right? Power up, divide by the power up. This part, I'm plugging in A and I'm plugging in 0, but I'm plugging in a number really, really close to 1 from the left. So like right? 0.999 minus 1 times the 1/3. That's really, really close to 0 to the 1/3. Then I plugged in 0 minus 1, -1 to the 1/3. Did the same thing over here. Right? You're plugging in a number really, really close to 1 from the right. This approaches 0. Both of those approach 0. So I end up with just 3, positive 3, right? Because this is -3 and this will be -1, so positive 3. And then this is 2 to the 1/3. There's nothing to be done with that. 2 to the 1/3 is not an integer, so and you don't have to write it as this radical. You could write it as 3 times 2 to the 1/3 as long as you don't write that as 6 to the 1/3. And I'm done. Did you get a number or an infinity? You got a number. And by the way, if one of these had been an infinity, then the whole thing is blown, right? Diverge. I don't care that if you write an infinity plus a number is still an infinity. This improper integral converges. All right, so that's it for, we'll do a couple more examples in our next live session, right? Improper integrals. Little weird. Just check out where your infinities might be showing. I'll see you in our next live session.